Hello, Precalc. This is going to be Unit 6, Day 4 today. In your packet on page 5, we're talking about more exponential growth and decay. Specifically today focused on population growth and population decay. And you'll see that the model we're going to be using today right below here is n of t equals n sub 0 e to the kt power. And although this looks pretty different than the formulas that we've used so far in this unit, I'll have you think about comparing this to PERT, because it really is the same thing. We use PERT when we're talking about financial applications where interest is compounded continuously, and this is essentially the same thing where n sub 0 is just like p. It's the initial amount that I plug in. So actually, you know what? I'm going to come right over here and fill that in. N sub 0 is the initial amounts, but here it was an initial amount of money. Here it might be an initial population, okay? And then if we're thinking about what A represents, A is the final amounts. So what does N represent, capital N or N of T? This is going to be the final amount as well. It's the final amount as time has gone on using that N of T notation. Well, what is T? Of course, T is going to be our unit of time. I'm not going to say time in years necessarily. Depending on the application, we might look at time in days, months, weeks, hours. It might be, depending on what we're looking at, time in a different unit than years. And then the e to the kt value, instead of saying e to the kt, I'm actually going to cross that off and just talk about what k represents. Because we know what e is. E is the base that's about 2.718 for the natural exponent. But k is going to be representative of either the growth or decay rate. And I'll tell you, if k is a positive amount, then it's a growth rate. But if k is negative, then we would say it's a decay rate. Okay. So what we'll find very commonly in these questions is that we're going to be finding e to the k first. So we'll have enough information to define what e to the k is in these questions. Once we know what e to the k is, then I can use it to answer a follow-up question. So using that logic, let's see if we can answer the following. Suppose that at the start of an experiment, there are 1,200 bacteria in a colony. Okay, 1,200 bacteria to start. Well, that's sounding like that n sub 0 in the equation above. 4 hours later, the population is found to be 3,600. So the way you would interpret that is n of 4 equals 3,600. Right, time is 4 hours. We're looking at 3,600 as the population. How many bacteria are there after 3 hours when the experiment has started? So I want to figure out what's n of 3. Now, because bacteria grow exponentially, we can't just think of this as being a linear model, like we're adding on the same number of bacteria every time. So in order to determine what the amount is after 3 hours, we have to figure out something about this growth and decay rate business going on over here. We're going to find that e to the k first. And we're going to find e to the k by using the information that we know about 4 hours later. So if I come to this formula, what would n of 4 look like? N of 4 would equal the initial amount, n sub 0, times e to the k times 4. So I'm specifically using data about 4. And by the way, notice that time was in hours, because if we're looking at bacteria, we're not looking at years. They grow very quickly, so hours later, we're looking at bacteria. All right, so I'm plugging in 4 for the value of t, and what I know is that n of 4 is 3,600. And I know that the initial amount, n sub 0, is 1,200. And I'm going to reverse that up there just because it looks nicer. We're going to say that's e to the 4k. All right, whole goal, like I said, is actually let's get e to the k alone, and then we'll use it in a follow-up question. So if I divide both sides by 1,200, we get that e to the 4k power equals 3 on this side. And once we've done that, I'm now going to isolate e to the k by getting rid of that 4th power. And how do I get rid of raising something to the 4th? You would raise it to the 1/4 power. Raise it to its reciprocal exponent. So e to the 4th to the 1/4, those kind of undo each other. It's now e to the 1st technically. So e to the 1k is equal to 3 to the 1/4 power. Now that I have that value for e to the k, I can come over here and say, oh, well, n of 3, which is what I'm looking for, would be the initial amount, n sub 0, times e to the k times 3. where time is 3. Well, n of 3 is what I'm looking for, which means that I know the initial amount is 1200 still. E to the k is 3 to the 1/4 power. So you're going to replace that whole thing, e to the k, with 3 to the 1/4. And what happens is that exponent of 3 that's already up there, we know that when you do a power to another power, that these things just get multiplied. So you could rewrite this as 1200 times 3 to the 3 times a fourth is 3/4 power. If you don't want to rewrite it that way, you can type that into your calculator as well. I oftentimes will just kind of clean that up a little bit and write the new exponent. So let's see if this is going to make sense to us. If I clear this out here and type in 1200 e, oops, I don't need e. I need times 3 to the 3/4. We already found e. 1200, 3 raised to the 3/4 power. We get 2,735. We're talking about bacteria, so we'll round it to the nearest whole number. So we'll say approximately 2,735 bacteria. Okay. So once I found that e to the k value, which has something to do with the rate of growth, then I could apply it in any situation, right? I could figure out how many bacteria there are after 100 hours. That would just be 3 to the 1/4 and then 2 to the 100 there. And we would use that as a model to be able to predict the number of bacteria, which would be a huge number at that stage in the game. But we can use this model to predict at any given amount of time, just based off of knowing what happens, at one specific time, which in this case was the 4 hours later. Let's look at a similar example. We'll move on from bacteria and talk about like real people now. Assume that the growth model above also approximates the Earth's human population in 1850. We're going to let 1850 be known as time equals 0. That's when we started kind of keeping track. In 1850, the population was estimated to be 1 billion. So at time equals 0, the population is 1 billion people, and that's the year of 1850. And then in 1930, it was estimated to be 2 billion people. So in 1930, we have to convert that to a new value of t. Well, 1850 to 1930, if I'm good at math, that looks like t equals 80 now, would be 2 billion people. Use the following data to estimate the population for 1980. So what do I want in the end? 1980 would correspond with t equals, well, that's more than 100. It's 130 years after the initial year of 1850. So basically, I want to figure out in the end, what does n of 130 equal, if that's my time? So we have to find e to the k first, just like in the last one. I'm going to use the information about 80 years to do that. We know n of 80. N of 80 would be the initial amount, n sub 0, times e to the k times 80. That's just using the general formula from up above, plugging in 80 for t. It's going to make your life so much easier just to leave this number as 2 and don't write out the 9 zeros that would follow, right? Just know that it's a number in billions of people, where the initial amount is 1, and then this would be e to the 80k. Well, the nice thing about having a 1 here is dividing 1 over doesn't change anything. This becomes 2 equals e to the 80k. And just like we saw in the last one, to get e to the k alone, we're going to raise each side to the reciprocal of 80, which is the 1/80th power. So therefore, e to the k equals 2 to the 1/80th power. Come on over to this side to figure out n of 130, which corresponds with the year 1980. N of 130 is n sub 0 e to the k times the time of 130. So this would equal the initial amount, which is the 1 billion people. E to the k we know is 2 to the 1/80th power, and that would be raised to the 130. It's completely up to you if you want to kind of suck that into one exponent there and multiply those out. It's going to be 130 over 80, which actually reduces to 13/8. By the way, multiplying that by 1 is not going to really change much there. So if I just do 2 raised to the, just to simplify my calculator steps, 2 raised to the 13/8 power, that's going to be 3.08. And I'm going to include that 0.08 just because we're talking about billions of people. So when I say 3.08, it's actually 3,080,000,000-ish people that many billion would be the expected population of Earth in the year 1980. So it's nice to be able to have models like this to be able to make predictions about the future. And as we get more and more data, the model may adjust from here to there, but we can use this exponential growth model to predict what's happening in 1980. By the way, I wasn't born yet, so if you're like, man, that was a long time ago, don't worry, I kind of feel the same way as well. Well, I was born in the 80s, so I guess it's not too long ago. All right, last thing we're going to talk about today is on page 6. On page 6, we're going to talk about half-life. Now, half-life is something you do learn in Algebra 2, but more specifically, probably talk about it a lot more in chemistry as well. So it says the half-life of a radioactive substance is the time required for half of a given sample to disintegrate. The half-life does not depend on the sample size. So whether you have 1,000 grams or 2 grams, it will take the same amount of time for your sample to decay or decrease to half of its amount. The most common example of half-life is the radioactive element carbon-14. Carbon-14 is used to determine the age of fossils because it has a really long half-life. It has a half-life of 5,730 years approximately. So you can imagine that if we know how much carbon-14 we would expect to have in a particular fossil, based on how much is there, we can determine that since the half-life is about 5,730 years, how old that particular fossil is. So this would be used to determine fossil age, most likely. I think they might even reference it in Jurassic Park or something like that. But if we need something that has a smaller half-life, for example, if we're talking about something in a hospital to diagnose a medical condition, we wouldn't want the half-life of that element to be 5,730 years. So hospitals use a radioactive substance called iodine-131 in diagnosing the thyroid gland. The half-life of iodine-131 is only 8 days, so that seems a little bit nicer than our carbon-14. If a hospital acquires 2 grams of iodine-131, how much of the sample will remain after 30 days? Okay, so let's talk about some of the things that we know. We know that the initial amount is 2 grams. So that's my n sub 0 equals 2 grams. And I know that the half-life is 8 days. So what I know is that n of 8 would equal half the original amount, which is now down to 1 gram. And if I know this kind of initial information, I can use this to find e to the k, just like we did on the last page, and then from there be able to figure out how much is left after 30 days. Now, just as a quick aside, we know that when time equals 0, we have 2. When time equals 8, it's going to be 1 gram. Another 8 days later, it would be a half a gram. Another 8 days later, it would be a quarter. And then another 8 days later, you would be at an eighth of a gram that's left, and an eighth as a decimal should be 0.125. So I know that 30 days later, if I do my math correctly, let me use some good English there too. If I do my math correctly, I should get an answer that's between these two amounts, according to all those half-lives. Okay, but I got to find e to the k. So n of 8 would equal n sub 0 e to the k times 8. And we know that 8 days later, the amount would be 1 gram since we started with 2 initially. Okay, just be cautious about this because we had 1 and 2 in the last problem, but remember they were on the reverse sides. So I got to divide 2 over to get a half. Oh, that makes sense because it's a half-life application. Equals e to the 8k. So therefore, e to the k is going to be 1/2 to the 1/8 power, right? That's what I would do to both sides to get e to the k alone. Come on over here and figure out, hey, what's n of 30 equal to? That would be the initial amount, which is 2 times e to the k times 30. Well, we know what e to the k is. E to the k is 1/2 to the 1/8 power. So that 1/8 and that 30 are going to get multiplied. If you want, you can make that into 38ths, or if you could turn it into 15/4, it's so up to you. But you also can just type that in as a 2 to the 1/2, or sorry, 2 times 1/2 raised to the, and then you could do 1/8 times 30. and that is 0.14865. So let's go to, I don't know, let's say 3 decimal places, 0.149 grams. So comparing my answer to what we thought should happen here, 0.149, definitely in between what we have 24 days later and 32 days later. So for these examples, you know you're on the right track if, following that half-life progression, you get an answer that makes sense, that falls into that range of values there, okay? I think if you're able to follow that example, you should be able to do this one on your own. So give it a try, follow the same exact logic as above for the half-life, and this one is just a general radioactive substance. We don't know which one it is, but I'm telling you it's 5 days. I gave you an initial amount. How much would be present after 12 days? So give that a try. Of course, we'll go over it next time I see you, but really like these questions. We're getting into some really good real life type applications that involve exponential growth and decay. If you have any questions, let me know next time I see you.